Okay, we're going to talk about 8.4, the limit comparison test. Often refer to this as the LCT. In the last section, I ended with this series, and I talked about how we sort of intuitively know that thing diverges, but we didn't have the tools to prove it, at least not by p-series. So what we're going to do today is we're going to compare it. Now, what we're going to compare it to is we're going to take a look at this series. And once again, the n equals 1, the same. It really is inconsequential. Those values can change. It doesn't make a difference. And I'm going to compare this to 1 over the square root of n, or n to the 1/2. Okay? And what I realize is for large numbers, these are going to act the same. So we already know this thing diverges by p-series. P is equal to 1/2. It's less than 1. Is that enough to say that this thing diverges as well? And actually, it turns out that it is. But we want to compare it, so what we use is the limit comparison test. So basically what I do is, I say the limit as n goes to infinity. It doesn't matter which one goes on the top. By the way, the 5 is inconsequential. I want to point out that the 5 I can bring out front anyways. It's just this n plus 1 in the denominator, or square root of n plus 1 in the denominator. So I can take 5 over n to the 1/2 plus 1 over 1 over n to the 1/2. And if I limit n to infinity, and I want to, I could do all the algebraic manipulation, but realize all this is going to be for large numbers is 5. Keep in mind the plus 1 and all that for large numbers is inconsequential if that's equal 5. So what that's saying is for large numbers, this 5 is almost meaningless. So either both are going to converge or both are going to diverge. So once I say this diverges, I can say this diverges, and that's limit comparison test. Okay? So basically, if I limit two sequences to infinity, sort of stacking them as a ratio, as long as that number is not 0 and is not infinity, then they can be interchangeable in our proof. They're either both going to converge or diverge. All right. Now, if I flip these, it doesn't make a difference, I want to point out. If I flip them, then I'm going to get 1/5. As long as that number is a real number, not infinity, and it's not 0, then they're either both going to converge or diverge. So let's write that up, and then we'll do the limit comparison. This is actually going to be quite a short video today. Okay, limit comparison test. So we have two sequences we want to compare. Both are non-zero, or excuse me, greater than 0. They're positive. I want to, once again, just reiterate what I said in the last section. Same was true with the integral test. We will learn ways of dealing with things if the sequence has negative qualities. Unfortunately, that's going to have to wait until the second semester. So what we do when we compare them is we limit them to infinity as a ratio, 1 over the other. Once again, it doesn't matter which one goes on top. As long as we get a value that's not 0 and non-infinity, then we can use those interchangeably in our proof. So they're either both going to converge or both diverge. Okay? And that is the limit comparison test. All right? So it really is an indirect proof. Sort of the logic here is we have a series that's sort of hard to prove it's convergent or divergent, but I can tie it to another series where it's easy to prove convergence using this limit comparison test. Okay, so we'll do a couple examples here. And that will be it for this video. Okay, so here's our first example. What I want to point out is this thing is going to look very, very much like the sequence I want to compare it to, which is going to be n equals 1, 3 to the n over 2 to the n, which is actually 3/2 to the n, which is geometric. Now, as we talked about with geometric, that first exponent is 1. The only time that really matters is if I'm trying to find the sum. Here, there's not going to be a sum. I know this diverges. So ultimately, I know this is a divergent geometric series. So I can tie it to this. So I would say, so we have a sub n, which is equal to 3 to the n over 2 to the n minus 1. And we have, that's greater than 0. We have b sub n, which is equal to 3 halves to the n, and that's greater than 0. Since the limit as n goes to infinity of a sub n over b sub n is equal to, and if we put this over that, the minus 1 will just drop out. That's equal to 1. That can be any number, non-zero. So since that equals 1, and since the series b sub n diverges by geometric, a little proof there. Absolute value of r is equal to 3/2, that's greater than 1. Then our series, a sub n, or 3 over 2 to the n minus 1, diverges by the limit comparison test. So it's kind of an indirect test. So basically the way this works is we have, basically there's always 3 statements. There's a limit statement, sort of tying them together. We do the proof with the easy to prove series, and then that leads to our conclusion for our series, either diverging or converging by the limit comparison test. And that is the limit comparison test. Okay, let's take a look at a couple more examples. Okay, so here's another one. This one would be quite hard to deal with, even with the integral test. But what I want to realize is for large numbers, since we have a degree 1 on top and a degree 3, the difference of those 2 degrees, it's going to act very, very similar to this series for large numbers, which is going to converge. So all I need to do here is go, we'll let our a sub n equal 2 to the n plus 3 over n to the third plus 1. Our b sub n is equal 1 over n squared. Both of these are greater than 0. Since the limit as n goes to infinity, a sub n over b sub n. Now what are we going to get here? What's going to happen is these are exactly the same, and you could do algebra if you wanted to. It's not really necessary. Why don't I go through it just to make sure we're all clear. So let's file this over. Limit as n goes to infinity. This will be 2 to the n plus 3 over n to the third plus 1. And then instead of dividing by this fraction, let's multiply by n squared. So we realize for large numbers, all these plus 3's and all this drops out. So this is just going to be like the limit as n goes to infinity of 2, like I said, the plus 3 is negligible for large numbers, 2n to the third over n to the third, and that's equal to 2. Now, right here, you can skip right to 2. I don't need to go through this. I'm just kind of making this point. So now we sort of tie these together. So we have that they sort of, for large numbers, going to act very similar. And since the series b sub n, p equals 2 is greater than 1, converges by p series. Then our series that we are interested in converges by limit comparison test. And that is basically it. Oh, I guess this was example 2, I think. Okay, and let's do one more, and then that will be it for this video. Really, the whole limit comparison test always relies on using another test. So it's just a matter of doing the comparing these limits to each other for large numbers. Okay, so let's talk about example 3. I'll give you one that's a little bit confusing here. Don't let these things be confusing. It should get to the point where you sort of see what you're going to compare it to quite quickly. Until then, you got to remember, we're talking about large numbers. So really the only thing that's going to matter, top and bottom, are the higher degree things. So if I'm trying to look at what this is here, what I'm going to compare that to, is I'm going to look at 3n on top, drop the plus 4. And then on the bottom, I'm going to look at the square root of 4n to the fourth. Everything else is negligible for large numbers. And then I can simplify this a little bit. So this will be 3n over, and then this will be square root of 4 is going to be 2, and then the square root of n to the fourth will be n squared. So what I need to compare this to for large numbers is basically 3 over 2. The 3 over 2 doesn't matter because it's just, you know, as long as it's a constant, it doesn't have to be 1. I'm going to compare this to 1 over n for large numbers, okay? If you wanted to compare it to 3 over 2, that's fine. But keep in mind, we're just trying to do p-series anyways, all right? So we can see this thing's going to diverge. So then we're going to write this up. So a sub n is equal to 3 to the n plus 4, 3 to n, 3n plus 4 over the square root of 4n to the fourth minus 2n plus 3, okay? Our b sub n is 1 over n. So then I go, since the limit as n goes to infinity of a sub n over b sub n is equal to, well, like I said over here, for large numbers, this is just going to go to 3 halves, okay, greater than 1. And since our series, or excuse me, the comparison series, 1 over n, p equals 1, diverges by p-series, and our series b sub n, no, a sub n, also diverges by limit comparison test. That's it, folks. That's 8.4. That's limit comparison test.